It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. Richard P. Feynman. This video presents experiments and observations that support the kinematics of light as a mechanical phenomenon. Observation of a star's orbit. Light emission as a mechanical phenomenon was applied to the observation of a star orbit. The figure depicts an actual star's orbit with the center at the point OS of radius r in the plane of the paper, and an imaginary circle of radius OA prime, with the center at the point O, and with its plane parallel to and in front of the paper plane. The distance d equals OOS is perpendicular to the orbit and the imaginary circle plane. The observer at rest is located at the point O. The observed star orbit of radius RO is centered on OS. The view is from the back right of the observer, which enables a clear image of the actual and observed orbits. The distances in each set of AA prime equals A second O equals EE prime equals E second O equals, and so on, and AO equals, EO equals, and so on, including all other similar distances corresponding to the points B, C, D, F, G, and H are equal. The waves emitted by the star in motion inherit the velocity v of the star corresponding to each orbital point and travel through different paths to the local observer O. At the point A, the star emits a wave front of light at the velocity c in the direction 8A prime, but this wave front travels along the path AO at the propagation velocity CSA. The direction and magnitude of the velocity c do not change along the path AO. At the point O, the observer observes the wave front originating from the point a second, traveling at speed c. At the point E, the star emits a wave front of light at the velocity c in the direction E prime, which equals A prime. This wave front travels along the path EO, which equals AO, at the same propagation velocity CSA. The direction and magnitude of the velocity c do not change along the path EO. At the point O, the observer sees the wave front coming from a point E second, traveling at speed c, along the path E second O equals a second O. The observer perceives a similar observation for each point in the circular orbit. The points A, B, C, D, E, F, G, and H give the corresponding points a second, B second, C second, D second, E second, F second, G second, and H second, points which offer in this particular case the observed orbit with the center at OS. The local observer sees the star's orbit rotated. This orbit has a larger diameter than the actual orbit, and the observed orbital velocity is greater than that of V. The observed circular orbit increases with increasing distance d. This observation compensates for the fact that objects appear smaller than they are as the distance increases. The speed of light from any point on the observed orbit to the observer is constant c. Therefore, no time irregularities exist to refute Ritz's ballistic theory, as de Sitter explained. Observing a star's orbit supports our understanding of the kinematics of light based on the ballistic law. Miller experiment. Studying the emission, propagation, and reflection of light in inertial frames helps us to predict zero fringe shifts for any location and altitude in Earth's inertial frame. This explains Miller's experiments at the Cleveland Laboratory in 1924, which employed light from local sources, as well as sunlight. The fringe shift with sunlight was of the order of 10 to the power of -8. The fringe shifts of 0.08 in 1921 and 0.088 in 1925, recorded by Miller using local sources at a high altitude on Mount Wilson, remain unexplained. Airy experiment. In addition to the interactions of the emission and reflection of light with matter, there are other examples, such as the velocity of light through a moving medium and the refraction of light when it travels from one medium to another, both at rest, according to Snell's law. Airy's experiment is an example of light dragging by a moving medium. Observing the star Gamma Draconis, Airy expected to adjust the inclination of the telescope after introducing a tube with water along its axis. However, this was unnecessary. Considering the dragging of light by moving water and the experimental results, we obtained the Fresnel dragging coefficient, 1 minus 1 over n1 squared from a mechanical perspective, where n1 is the refractive index of the medium. Majorana experiment. Majorana's experiment in Earth's inertial frame employs a fixed light source. The light travels through 3 stages, each consisting of one movable and one fixed mirror, and enters a Michelson interferometer with arms of unequal lengths. The movable mirrors are fixed in both directions on a rotational disc. A fringe image is observed when the disk is at rest. When the disk is rotated from maximum speed in one direction to another, a 0.71 fringe shift is observed. Similar to the Michelson interferometer, Majorana's experimental device offers an outstanding contribution to the physics of light, despite changes in the interpretation of the experiment over time. Majorana misunderstood the phenomenon within the device and the significance of the fringe shift observed during the experiment by explaining the fringe shift as supporting special relativity. The reflection of light as a mechanical phenomenon applied to the Majorana experiment proves that the speed of light changes after each stage, causing a fringe shift in the Michelson interferometer. Approximating rotational mirrors as inertial frames, we derived a shift of 0.27 fringes. However, both fringe shifts confirm the kinematics of light, rejecting the constancy of light propagation.